Hello everyone, so welcome for this today's session. So in the last session we have seen the basic postulates of the quantum mechanics, and in continuation to that we will see that the next topic, that is a Schrodinger wave equation, because we all discussed that in the last tutorial that a particle can have the dual property that it can act as uh, the photon, also it acts as the wave. So now this wave phenomenon is described by the Schrodinger wave equations. So now let us see this little small derivation. Let us hit back to the screen. Okay. So to start with the Schrodinger equation, we will consider a particle. We will consider a particle which has the potential energy V of x, y, z. So why? Because when we are talking about the potential energy of a particle, here the particle is in the three-dimensional space. So that is why where V represents the potential energy and this represents the dimension in which it is exists. And we consider that this particle has certain momentum P and has some mass m. And now let us consider the total energy of this particle. So the total energy of the particle is given by, we know that it is the sum of potential energy plus kinetic energy. So now we know this is the potential energy in a three-dimensional space. So it is V of x, y and z plus the kinetic energy, we know it is P square by 2m. So let me rearrange this equation. Then I'll consider this E is equal to P square by 2m plus V of x, y and z. Okay. So we know that the P is the momentum. So this is nothing but the momentum of the particle. And since this momentum is not restricted to two dimensions, it is a three-dimensional momentum. So we will consider that the momentum P square in the three dimensions. So I can write this P square as Px square plus Py square plus Pz square. And from the basic postulates, so from the second postulate we have seen that the state function is operated by an operator. So there we had written, so let me take you there. So here we have in the basic postulates, in the postulate 2 we have described the various dynamical variables and their operators, the quantum mechanical operators. So here if we see the momentum Px has this operator, that is h hat by j with the derivative of x. So same thing we will consider here. So considering that operator, so here it is Px square. So if we square it, okay, let me write here first. So Px is equal to minus h hat. Sorry. So let me erase this. So it is minus h hat by j, the partial derivative with respect to x. So this is the operator for the dynamical variable of Px. Now if we square this, what happens? Since j is in the denominator, so j square we know it is minus 1. So since it is in the denominator, when you take it to the numerator, it becomes plus 1. So we have here, so it is minus h hat square with derivative square with respect to x square. Now if we substitute this in this equation back here for the kinetic energy, so what we get is we get here this as minus h hat square by 2m with gradient square, where gradient square is nothing but it is the derivative of all the three-dimensional space. So this I can write this as the partial derivative with respect to x square plus partial derivative with respect to y square plus partial derivative with respect to z square. So this is the gradient. Then finally, if I put back all this in my energy equation, so this equation will become, so this will be, now E is equal to minus h hat square by 2m with the gradient square operating on the state function. We know this is the state function plus the potential energy in a three-dimension, that is V of x, y, z operating on the state function. So now from the again second postulate, we will take the operator of the energy. So if we look back here, so the operator for the energy, the total energy is given by minus h hat square by j into d by dt with respect to time. So now we will apply the same thing here. So then we will get this as, so let me write to the right hand side. So it is h hat square by 2m. I'll take the energy onto the right hand side. So it's a gradient square operating on the state function plus v of x, y and z, and this is psi, which is equal to minus h hat by j with a partial derivative with respect to time, and here the partial derivative of the state function with respect to time t. And let us call this as equation number, okay, we are not given any equation number, okay, let us call this as equation number 1 here, and this equation is nothing but the Schrodinger wave equation. So this is Schrodinger wave equation. So with this equation, we can understand the potential energy in terms of the quantum mechanics, and it links to the real world application. Now let us consider the total energy of a system which remains to be a constant. So let us consider a system, a conservative system, in which the total energy of the system remains constant. So the total energy in this system remains constant. So this is nothing but if you consider an example here, so you can consider the motion of particle in a static field. It is a motion of particle in the static field. Motion of particle in the static field of force, and the motion of electron and the motion of electron in an hydrogen atom. So this you can consider this as a typical example where the motion of the particle in a static field of the force and the motion of electrons in the hydrogen atom. So now let us consider the potential energy V as the independent of time, and using the method of separation of variables, so in system like this, in a system like this, let us consider the potential energy. The potential energy V is independent of time, then we express the state function as not only with the 3-dimension. When it is independent of time, then we can write along with the 3-dimension with the time t. So then this can also be written as the state function with 3-dimension, that is x, y, z, and the t can also be written as the phi of t. Let us call this as equation number 2. Now if we substitute this for gradient psi operator in the equation above, so if you see here, so we have this term here, the gradient square state function psi, and if you apply this equation 2 into equation 9, then what happens is, so we will get the final terms of the energy. We will get this as h hat square by 2m gradient square psi by psi plus v of x, y, z, which is equal to, the right hand side is the total energy, that is minus h hat j into 1 by phi d by dt of phi. Let us call this as equation number 3. Now if you consider this equation on the left side is nothing but, this is the function of space coordinate, whereas the right hand side is a function of time. So now both of these functions should be equal to something. So it should be equal to some constant. So with that results in the two simple differential equations. So this both should be equal to some constant E. So we'll just consider the constant which is equal to E, and this will result in the two differential equations. So then we will get this as the gradient square psi plus 2m into 2m by h hat square of E minus V with the state function which is equal to 0. Let us call this as equation number 4, and the other solution which we get, the other differential equation which we get is the minus h hat j phi of d by dt of phi, which is equal to E, some constant. Let us call this as equation number 5, where E is nothing but the total energy of the particle. And whereas the second differential equation here, it is the time dependent equation, because if you see, it is the derivative with respect to t, time t, therefore it is a time dependent equation. Now if we integrate the second differential equations on both sides, since the equation 4 is the time independent, whereas the state function is time independent of the wave equation, and let us integrate this both side of this equation 5. So then I'll get this as j phi with d by dt of phi, which is equal to integral of E, and then we will get the solution as phi of t, which is equal to a into exponential of minus j e t by h hat. So let us call this as equation number 6, and the wave equation in a 3-dimension can be written as psi of x, y, z and time t is a psi of x, y and z which is an exponential multiplied by an exponential, that is exponential of minus j e t by h hat. Let us call this as equation number 7. So in general, this can be written as the psi is equal to summation of n equal to 1 to n a n psi n x y z into exponential of minus j e n minus e n t by h hat. Let us call this as equation number 8. So here the terms a n is constant and psi n is nothing but the solution to equation number 4. Solution to equation number 4, which corresponds to E is equal to En. So when we talk about the potential energy here, so we will see this when we talk about the harmonic oscillations, that I'll not go in much in detail as of now, but if you see this, the energy in terms of the classical mechanics, the potential energy is something like this, which looks like this. So if you take some points here, that is minus x naught, and here this is x naught, so then the potential energy becomes 0 when x naught is equal to 0. But whereas in case of the quantum mechanics, that is not true. The energy level, the potential energy will never be 0. Okay, so you will get something like this for the first energy level, and the second energy level we will get like this, and so on. So this we'll talk in details when we talk all these things. So finally, this equation, what we have seen, is called the Schrodinger wave equation. So that describes the wave motion of the particle. So that is what we need to understand here. Now continuing our discussion with the free particle. So let us now discuss about what is a free particle. So a free particle is one which moves in the space which doesn't have any influence of the external potential or any external force. So such a particle, we call it as the free particle. So if you look into the formal definition of the free particle, then it is something like this. It is the particle moving in a region of constant potential energy and it is not subjected to any force, and it is called as free particle. So let us consider the moment of this particle. If we consider this is the free particle, let us consider the moment of the free particle with respect to one dimension, that is in the x-axis. And if we consider that the particle is moving in this direction, that is in the x direction, then the potential energy is very random, and we take the potential energy at this point is equal to 0. Then from the differential equation of the Schrodinger that we have done before, that is from the differential equations. So if you see that we got the two differential equations here. So where is that? Yeah, here. So equation number 4 and equation number 5. So by considering the differential equation, that is equation number 4, so we'll write this, the free particle, as the equation number 4. Let me rewrite here. So that is the gradient square operating on the state function plus 2 into mass h hat square of energy minus the potential energy. So we represent the potential energy here, which is equal to 0. So this equation can be written as the second order differential equation. So therefore it is d by dx square. We have taken this as the x square because it is on the x-axis. So it means the state function is on the x-axis. So that is why we are differentiating with respect to x plus k square state function operating on the state function. Let us call this, let me continue the numbers here. So it is 8. So let me call this as 9. Okay. Where k is nothing but, from the above equation we can write it is the square root of 2me by h hat, which is equal to the mass into acceleration. We know that it is kinetic energy is nothing but mass into acceleration. It can be written as it is nothing but the momentum. So this is a momentum which is equal to, it is 2 pi by lambda. Let me call this as 10. So now we have related this, the momentum and the Planck's constant, with the wavelength lambda, 2 pi by lambda. So if we solve this equation number 9, so then we get the solutions for the psi 1, which is equal to a 1 into exponential of plus or minus j k x, and psi 2 of x comma t is equal to a1 into exponential of j plus or minus kx minus omega t, which is, let me call this as equation number 9, and where omega is nothing but it is energy by h hat, which is equal to h hat k square by 2m, right? So we'll get these state functions, that is psi 1 and psi 2. So here there's equation number 19, the equation number 11, it states that the wave function, it represents the wave function is in the stationary state. It is in the stationary state and is a eigenfunction of momentum and energy operator. It's eigenfunction of momentum and the energy operator. So if you consider that in the last tutorial we had written the probability density function, that is the state function, and its conjugate can also be written as a into a conjugate, and it is independent of, let me write correctly, it is independent of x and t, it means the direction and the time, then it means that the probability of finding a particle is same everywhere, and the wave function conveys no knowledge about the precise location of the particle. So it means we can say that with this, the particle is everywhere and the wave function cannot give a knowledge about where exactly the particle exists. Okay, so this is what the free particle. So now let us talk about the harmonic oscillations of this wave particle and compare this with the classical mechanics. So if you talk about the harmonic oscillations, harmonic oscillator. So the harmonic oscillator is nothing but, if this is a particle and let me write another figure rightly. Yeah. If all the forces acting on this particle is equal, that means it is in the equilibrium position by the force, uh, the particle is in the equilibrium position, and by any force that is directly proportional to the displacement. If any force is exerted on this particle and if it changes its position, it means it's displayed, then its motion or its position executes a simple harmonic motions. So the motion of this particle from this position A to position B, it represents the harmonic oscillations. Harmonic oscillation. So hope you understood. So let me tell you again. So the particle is at the equilibrium position. It means all the forces acting on this particle is same. And if there is any additional force which is exerted on this particle and this particle is displayed from one position to the another position, then the motion is described by a harmonic oscillator. So that is what the harmonic oscillator. And the small amplitude motion um, of the pendulum can be considered as a typical example of this. And this is very important to study because it gives us the understanding of mechanical vibration in the lattice. So lattice is nothing but the arrangement of the crystalline structures. So lattice can be something like this, which are perfectly aligned. So if these are atoms and these are perfectly aligned in a systematic structure, so like this, like this, so like this. So this is the lattice structure where atoms are perfectly arranged. So there are other definitions of the harmonic oscillator also exist. So the other definition is that the harmonic oscillator, let me take you here. So the other definition of the harmonic oscillator is the harmonic oscillator, whether it is in a quantum mechanics or in the classical, is a particle in a potential energy well with V of x equals half k x square, where k is the force constant, and it can be seen as the motion of small mass attached to the string. So it means if we have a spring here, which might be a high tension spring or whatever, and if a mass is connected to that, and if the mass is released, if the position is released, then what happens? This spring expands depending on its tension, or it also depends on the mass, how much weight it has. Then what happens? These oscillations up and down will represent the oscillation moments, the harmonic oscillation motion of a parabolic shape. Okay. Now let us consider a particle of mass m. Let us consider a particle of mass m which executes simple harmonics along the x-axis. Then the force acting on this can be defined as derivative of with respect to x. So here we are talking with respect to potential energy, because here the atom is at the rest, it is at the equilibrium position. It means it is in one position, it is not in the motion. So only when the force is exerted on this atom, then it changed its position from A to B, and then its motion is represented by an harmonic oscillations. So that force, we define that F is equal to minus d by dx, because it is moved in the x direction with a potential energy V. So this can be represented as minus gamma p x. The potential energy of the particle, V of x can be written as the gamma p x square by 2, and the total energy E, we know that it is the sum of the potential energy plus kinetic energy. Then that can be represented as, so this is our potential energy, so substitute here, it is gamma p x square by 2 plus the kinetic energy, we know it from the Schrodinger wave equation, it is p square by 2m. So call this as some equation, so let me call this as equation number 13. Okay, sorry. Okay, so if you consider the classical equation of the motion of particle is obtained from the Newton's second law, it means the classical motion or the classical equation of motion of particle is obtained with Newton's second law. So what is the Newton's second law states? It states that the acceleration of the object is dependent on two variables, that is the net force acting on the object and mass of the object. It means the acceleration, if the mass is smaller, then the acceleration is directly proportional to the force applied to it. If the mass is heavier, then it is inversely proportional to the force. So then differentiating with respect to time, the x-axis, which is equal to omega naught square x is equal to 0. So let us call this as equation number 14, where omega naught is equal to root of gamma p by m, which is equal to 2 pi into v naught, where v naught is the frequency of oscillation. If you solve the equation 14, then if we solve the equation 14 here, so we will get the x, the solution to x is equal to a naught sine omega naught t plus theta naught. Let me call this as equation number 15. So you can see from this equation that in the quantum mechanics, the movement or the motion is sinusoidal. The motion is the sinusoidal. That is what it is important. So to understand this, let us look into the waveform of these harmonic oscillations. So if you look into this first waveform here, so this represents the energy equation with 2 points here. The function of this is with respect to the classical motion of the particle, where Vx defines the potential energy. Now at x is equal to x naught, what happens? The potential energy here at this point is equal to 0 and the kinetic energy is maximum. And when it comes to this point, whether it is minus x naught or plus x naught, then the potential energy is maximum and the kinetic energy is 0. But whereas if we compare with the equations which we have developed right now, that if it is a O written on the classical wave motion, then the quantum mechanics solution states that the energy cannot be 0. So whereas in this case you can see here at x equal to 0, Vx is equal to 0. It means the potential energy is equal to 0. Whereas in case of the quantum mechanics, the potential energy cannot be 0, because when we write this on the energy band diagram here, or the energies, so then we will get this here like this, the waves. If you see, even if you see the at n is equal to 1, n is an integer, so at the energy level 1, so you seem to be here 0, but that is not 0. If you look into the y-axis, it is not 0 here. So it means the potential energy will never go to 0. Okay. So this is the wave equation, and that we have obtained from this sinusoidal equation, that is for x directions. So continuing with our statements, then the classical turning point at these can be written as, that is E is equal to V of x naught, which is equal to gamma p x naught square by 2 where x naught is equal to plus or minus root of, it means the same equation is rearranged. It is gamma p. Let me call this as equation number 16. Now if we take the Schrodinger wave equation, that is the second equation, same thing again. If you write here, that is h hat square of e minus v, which operates on the state function, which is equal to 0, then this equation becomes, it is d square with respect to, since we are operating on the x-axis on the state function, then it is 2m by h hat square of e minus gamma p x square by 2, which operates on the state function again, which is equal to 0. So then solving this equation, let me call this as equation number 17, and if we solve this equation, then we get an energy E, which is equal to n plus, this is n plus half h into v naught. So when n is equal to 0, even at the 0 energy state, when n is equal to 0 here, then what do we get? E is equal to half h v naught. So it means if you look into this equation, if you look into these waveforms, even at n is equal to 0, we have the oscillations like this, and where the potential energy is not 0. And when n is equal to 1, it is like 1 plus half of h into v, so we'll get these kind of waveforms. So this is what is important to understand. So in classical mechanics, it is considered that it is a parabolic shape of this at the 2 points, at some 2 points, that is at from x naught minus x naught to plus x naught, and this is 0. So what happens is that, so this is the graph representing the potential energy V of x, and this is some energy here which is higher. So with respect to this, it says when the particle is moving and when it reaches the point, say x naught, its potential energy is, the kinetic energy is 0. When x is equal to x naught, its potential energy is 0 and kinetic energy is maximum. When the particle is at these points, which is at minus x naught or plus x naught, the potential energy is maximum and kinetic energy is 0. Whereas that is not true in case of the quantum mechanics, because quantum mechanics has the wave-like motion. So like this, and then with the other energy states, which is like this, and then for higher energy states we have the oscillations. So these are the harmonic oscillations which are generated in the quantum mechanics. So that's it for today's session. So in the next session we will talk about the hydrogen atoms and the arrangement of the periodic table and the other things, the orbitals and all these things. So thank you for watching this session.